Professor Amitabh Ghosh does not need any introduction. He is well known to all of us. But as a ritual, I am privileged to introduce him. Born in 1941, he is the former professor and head of the mechanical department at IIT Kanpur and also former director of IIT Kharagpur. He was also chairperson of CSIR Central Mechanical Engineering Research Institute, Durgapur from 2001 to 2013 and also chairperson of NITTR Bhopal from 2009 to 2014. He also chaired a number of national level committees like FIST of Government of Science and Technology, Government of India, Engineering Sciences Committee of CSIR. He was also Indian coordinator of Indo-Japan Science Collaboration Program run by the DST and GSPS from 1998 to 2007 and Indo-US Joint Center for Research Excellence in Manufacturing from 2006 to 2013. Professor Ghosh has written 13 books and textbooks written by are widely followed in India and abroad. Currently, he is an emeritus scientist of Indian Science National Academy, New Delhi. He is a fellow of all 4 science and engineering academies. You name it, he is the fellow. Fellow of Institute of Engineers, fellow of National Academy of Engineers, fellow of National Academy of Sciences, and fellow of National Academy of Sciences. And it's our privilege to invite Professor Ghosh to give his keynote lecture.
Thank you. Thank you very much. To begin with, I convey my most sincere thanks to Professor Kumar and the organizing team of AIMTR 2023. And I also apologize that although initially I had all intention to be physically present, but something came in the way, an unavoidable circumstance for which I am not able to be physically present amongst you and enjoy your company. I have a long association with AIMTR, starting from the very first one, which I also was a member of the organizing team. Then, of course, subsequently, I attended many AIMTR, Durgapur, Roorkee. We organized it in Kanpur in 1980 and also attended AIMTR in many other places. So, I feel very happy to be amongst you, though virtually, thanks to the technology and thanks to COVID. Because of that, only we have been forced to adopt these technologies. So, I think today's topic, when I was requested to give a talk, I said that I will talk something from an academic point of view. That is, actually, you are familiar with that it is often considered that manufacturing is not that intellectually challenging a scientific activity. So, which I think that kind of a wrong impression should be dispensed with. And I will tell something today which is primarily keeping in mind that what is going to happen in the distant future, not too distant future, I would like to say. So, I think if you allow me, I will share my screen and present it in the PowerPoint form. So, as you see, the title I have kept as Engineering Science, its role in innovation and translational research in manufacturing. Now, this term translational research is of relatively very recent origin, and its relevance have been in the case of primarily medical and biomedical research. As can be guessed from the English meaning, translational research, it means direct transfer of useful results from the laboratory to the application area. In the case of medical research, quite a few stages it had to cross a discovery before it could be allowed to be applied. So it used to be a long gap, but that's why the effort was quite strong and people tried to develop methods or the approach by which a quicker adoption of the laboratory developments can be possible. And that's how the translational research term came. But the idea of using the philosophy of translational research in engineering has been very recent, because people thought that translational research can help innovation and a faster progress of the company. Now, since many of the concepts are still not very mature. The topic is to some extent nebulous in character. But an attempt is being made in this talk to understand its link with what is called engineering science. Now, this term may not be unfamiliar, but its implications are not always very clearly understood. And my objective is to the designer of the new curricula in the coming days to be aware of this phenomena and to adopt the necessary changes. So, however, it should be remembered that the involvement of scientific principles is often not through its raw form, but by a middleman, which we can call engineering science. So, I'll give examples and explain it in more detail. Now, the importance of engineering science should be properly recognized, and how it helps to progress and innovation needs to be formally recognized. This recognition helps in framing various curricula, as I just mentioned, and training programs that can lead to major innovations in manufacturing that may usher the world into the realm of the next industrial revolution. Now, to understand the presented material better, first we have to have a quick look at the fundamental characteristics of science, engineering, and technology. Now, I must caution that all these three terms has two aspects. One is the definition as a subject, and another one is the activity. So both I would like to address. Once these relationships are understood, it will be easier to grasp the basic nature of engineering science as a body of knowledge. So science. What is science? The word science originates from the Latin word scientia, which means knowledge, knowing, creation of new knowledge, etc. etc. Now, an example I can give you. You are all familiar with that. So when an electron is at a higher energy level, it can spontaneously come down to a lower level, as can be seen, and this energy is radiated in the form of a photon of suitable frequency. According to relation, E is equal to h nu. Now, this is a spontaneous radiation. Another kind of radiation is possible where an excited atom is here or electron is here, and a suitable photon impinges on it, whose energy is exactly same as the difference between this level and this level. So what happens? That this electron falls to the lower orbit, emitting a photon which is exactly same as the impinging of the photon which has stimulated this radiation. This is called coherent radiation, and this phenomena is called stimulated radiation. So this is a phenomena which was discovered by the physicists. So this is science, discovering a new phenomenon of nature, a new law of nature, such things. But then, what is engineering? Engineering word originates from the Latin word ingeniare. That means to innovate, to contrive, to devise, and such creations come directly from basic science. It is also related to Latin word ingenium, implying cleverness. So engineering is primarily the innovation. You take the basic science and apply your innovative skill to make it something which is useful. Thus, when the basic science of stimulated emission is employed for practical purpose, just in a raw form, a stimulated emission has no use. But then what is done by engineers is like this. That is, if a photon emerges a stimulated emission, then there are many more electrons, and they all undergo stimulated emission, and this waves back and forth between two parallel mirrors, and ultimately a very strong coherent beam emerges because of these millions of to and fro motions of these photons. That means this is the way that the stimulated emission can be used to get something you can get which can be used. So we get a very strong coherent light which we call laser. The stimulated emission is not laser, obviously. So this is actually engineering. Innovation is involved. And once an extremely powerful coherent light beam is produced through engineering, its application to various real life work like manufacturing, communication, material processing, etc., is the activity we call technology. So this is the hierarchy. So technology word originates from the Greek word technologia, which means systematic use of craft, art, etc. So it is more practice oriented. So it is also related to Sanskrit word taksan, which I will not discuss in details. But so therefore you can see the hierarchy. Science is the pure knowledge. Then it is innovated in a manner so that it can be utilized, that is engineering, and then its application to various fields is technology. Like a laser beam can be used for welding or drilling, cutting. You are all familiar in manufacturing area. So therefore, activity-wise, science is what? It is an activity whose basic feature is analysis, using the capability to observe the nature and understand the various phenomena. On the other hand, engineering as an activity, its basic feature is characterized by synthesis, using the capability to innovate. Science, what is the output of science? Output of science activity is new knowledge and understanding, better understanding. Whereas the output of engineering is products, both physical and non-physical. Now, I think this is fine, but now the question comes, where engineering science stands as an activity. Now you can see these are both activities and these are all body of knowledge. So engineering science can be considered as a body of knowledge, but where it stands? Now this is diagrammatically can be explained. The basic science in its very raw form. Now science in its usable manifestation, that is called engineering science. I'll give examples. From there we directly go to engineering and there to technology. One or two concrete examples as I mentioned should be given. Say, for example, consider a very large number of atoms interacting very strongly with one another. The overall result is some relations between the external forces, the control volume deformation and failure, and the subject providing these gross characteristics we call solid mechanics. But it starts from the interaction of individual atoms. Similarly, consider a very large number of atoms interacting somewhat weakly with one another, and the overall result is some relations between the external forces, which we call pressure, and the control volumes deformation and displacement. And this subject providing the gross characteristics we call fluid mechanics. So as you can see, both starts from physics, but their manifestation is somewhat different. And we don't, when you try to design a bridge, you don't see the interaction between individual atoms of all the components of a bridge. We take the aggregate information or the basic manifested form of this, which we call solid mechanics. So the following slides also show some examples of applications, and all these can be possible only when a strong understanding of the relevant engineering science exists. This helps in innovation and perhaps in translation research. Why I am emphasizing this point, dear friends, particularly those of my colleagues in the academia, there is a trend now to find that slowly the subjects which we call fluid mechanics, solid mechanics, thermodynamics, they are gradually being pushed out of the main curriculum, and their importance which we give in teaching is gradually getting reduced, and that is the danger. So I think because here if we give too much importance to only technological part, that is the application, which starts after the engineering has taken place, then it will be difficult to innovate newer engineering, because all engineering actually depends on the engineering science. So I think we should be careful if we we have to make our engineers of the future capable in innovating and discovering new things, I think we should not, rather we should include more and more new engineering science subjects, which I will give examples later. Say, for example, this molecular dynamics rate. Now we have big computers. So all these things have become possible. Earlier it was not possible. So you can do molecular dynamics analysis, and through that you can find out the various properties, and there are many new subjects are coming, approaches are being developed, so that way you can get some aggregate characteristics. You get some properties also theoretical. So for example, if we apply dislocation dynamic modeling to study the effects like water hardening, etc., you can all find out theoretical. So similarly, multi-scale computational mechanics, which are now very interesting subjects. You start from atom, you can go to the single crystal. You can also theoretically identify its microstructure, its strength, its deformation characteristic, many physical characteristics you can theoretically predict. And as a result, you can see, for example, where our manufacturing starts. Understanding the fracture mechanics of hard and brittle materials and tough and ductile materials led to the development of ultrasonic machining using the application of vibration. You all know, you are familiar, the tool we make of tough and ductile material, and the workpiece is like something with glass, which is brittle. So therefore you know that this the erosion process will be in this on the tool, and you can produce some shapes in this way. Similarly, when understanding an appropriate application of the theory of selective analytic dissolution, this led to the development of electrochemical machining. We are all familiar. Again, we know that a better understanding of gas evolution and bubble formation helped in developing a hybrid process we call electrochemical discharge machining. Like that, actually, it is the basic understanding. If you don't understand the difference between hard and brittle materials fracture and tough and ductile materials resistance to fracture, ultrasonic machining you cannot develop properly. So now, of course, machine learning and all these kind of new subject is coming up. They are calling virtual alloy. So you can design a material theoretically, everything by atom, and which will give you exactly the desired properties, and you can create an artificial material according to your prescription. You don't have to do unnecessary trials, mixing this much, that much, all things can be avoided. Now you can see fluid mechanics governing equations. Through molecular dynamics in microscopic scale, mesoscopic scale, we keep this lattice-Boltzmann method, and then ultimately you get the Navier-Stokes equation. Something like solid mechanics, you get this constitutive equation, stress-strain relationship. So you get the Navier-Stokes equation. So when you solve the fluid mechanics problem, it can be addressed from the molecular level to mega-scale computer simulation. But more convenient way will be to use the Navier-Stokes equation, as we all do. Say, for example, if our understanding of fluid mechanics is complete, what we do, we only look into the large scale, mesoscopic scale things. But if you go to the microscopic and nanometer scale, we find many new properties and characteristics can be understood, which can lead to a new branch of fluid mechanics, which we call microfluidics. And it has a huge number of applications in biomedical devices, in many other areas, and so therefore it is not possible unless we understand the engineering science part of fluids motion. Say, molecular simulation also can do in polymer. The thermophysical properties of polymers can be determined theoretically. Actually, this helps. You can design your own polymer exactly, less like designing a shard or somebody's shoe. You can design your polymer prescribing exactly what kind of thermophysical properties you want. And you can do it, you can develop that polymer, no experimental trial and error method is required. That way what happens, if you just depend on your trial error, many interesting things may be missed. So, but if you have a complete idea about the whole process, no such occasion will be there where you miss something very interesting and important. So, for example, another very important thing is gradually becoming important. You know that a surface can be made hydrophobic. That means which tries to avoid contact with water. Another way is that you can make a surface hydrophilic, which will always actually hanker for water, thirsty for water. You would like to be contact with water. So you have all done this in your bubbles or your other kinds of surface tension or phenomena. So understanding interactions of fluid molecules can help in designing hydrophilic and hydrophobic surfaces. Why that becomes important in manufacturing, I will show you now. Now, proper manipulation can lead to successful self-assembly of materials. That is considered as a major goal for futuristic manufacturing. Now, some basic idea, now we are thinking of going from top down to bottom up approach, where we just place atom by atom to develop something, but it cannot be done from outside because it will be enormously time consuming. Even to fabricate a 1 micron by 1 micron cube, it will take tens of decades. It will take if you do it within 1 microsecond. You take to manipulate 1 atom. So the only way it is possible is that let the material self-assemble itself, and that can be done if you can understand the hydrophobicity, hydrophilic nature of surfaces and how to make them so. So what will happen is like this. Suppose when there are components you have prepared, say basic bricks for example, which interact once they come in contact when they are suspended in a fluid and there is some agitation, thermal motion, they come and they get attached. But if the attachment is too strong, then what will happen? Something like this, another comes. So this gives rise to a very amorphous object without any definite geometric shape. But if the systems are such that this contact here is not that strong, but it can adjust if necessary. So what happens is if the surfaces are hydrophobic and they are in water medium, so they will always try to adjust its surface area in contact with water is smallest. So therefore what will happen? This comes. Now you can see these are the exposed areas to water. It will try to reduce that area and becomes like this. So if there is another one comes like this, but then again it will adjust. So this way you can see it always tries to minimize its surface area which is in contact with water. You don't have to do anything. So this is the basic process of self-assembly of material. Now, so for example, this is already being used in drug industry. A lot of medicines are designed that way. Say for example, if you want some particular type of surface, suppose what you do, you take the molecules, one end of the molecule is a hydrophilic functional group, it does some work which you are interested in, and there is one end which is hydrophobic carbon chain, which will avoid water, but it is not having any function. If you build trillions of such molecules, if you have to organize so that all the functional side is on one side, it is possible very easily if you do it by self-assembly like this. You just throw it on water. Immediately all the hydrophobic ends will go up and hydrophilic ends will be there. If the density is a bit more, then it can be a bilayer where all the hydrophobic ends are trying to minimize their contact with water. They are hiding their face. Just the way the ladies sometimes hide their face in the villages. And with some other density, you can form mishens where all the molecules the hydrophobic ends have gone inside and only the functional hydrophilic ends are outside. So this can be a trap where this functional outside layer does some work. So this is the way CLFS will work. Now it is at molecular level, but gradually it is increasing inside. So for example, you have your basic element in the form of a hexagon, a two-dimensional case say, and the alternate surfaces are hydrophobic and alternate are hydrophilic. So more, if you throw them in water, what they will do, all the hydrophobic ends will try to connect with each other so that the contact with the water is minimized. So this kind of shape you can generate automatically. If all the faces are hydrophobic, then the kind of shape it will generate will be like this. Suppose if this is the basic element and you have designed this as hydrophobic ends, then they will try to automatically come together to reduce the contact with water and the kind of shape you generate. Like you can develop, say, very special type filters, etc. You can develop in this way. This is just some small example. Now, the understanding of this manifested form of the basic science can be used by engineers for developing processes, systems, etc. Now, engineering innovation yielding newer technology is a key requirement for progress, and for the progress of economy, such continued innovation is essential, as only innovation can result in appropriate value addition. This is something quite often is missed in our discussion, value addition. Just making something is not important. It is important that how valued it is. I'll give an example. Say, to attain economic superiority, this value addition is important. In India, we make lots of motor cars. And once, I think, Indica car became very popular in East European countries. So, India is to export. So, you can see our export. So, we send 500 Indica cars in 5 ships. And we earn how much? Each Indica car gives you 4 lakhs in those days. So, about 20 crores you get. USA sends you, when you have money, eventually is Minister of Education is kind to you, you get one helium ion microscope, just in one box, 1.5 meter by 1.5 meter. That costs 20 crores. So this is, and unfortunately, in our economy, this value addition is not as expected, not up to the mark. So, like even our software, what we export, they are not very high value software. It is very low value. So, what you can to do value addition, you need innovative capability, and to innovate, to add value, you need engineering science. So, in order to address the above mentioned problem, it will be necessary to achieve many innovative transformations of the existing processes through which things are designed and manufactured. You know there are lots of processes. Thus, it may not be totally out of place to mention just a few points related to manufacturing. How much time do I have? 10 minutes? Hello? Okay. Once manufacturing left its earlier garb of craft and became a part of engineering, its relation with science became intimate. And you remember those, the real research in metal cutting, etc., started in 1940s. Before that, it was mostly a craft. But with Marchand's single salesman theory, we had at least some understanding of the chip formation process. Though it is now considered so primitive that we don't even discuss that. But before that, it was not even there. So, that the progress of manufacturing became closely linked to the progress of science. And to chart out an optimal route to the futuristic manufacturing activity, it may be desirable to understand the concepts involved in the whole range of activities we call manufacturing. So, manufacturing, management, country's economy, all these things you know. Now, materials, from that we raw material, we get the tools, dyes, and also the work material. We have the primary processes. In mechanical engineering, it gives us relative motions, drives, control, machine tools, material handling, etc. And so, the combined way, we get the secondary process, then assembly and finishing, and finally the product. This is the basic relationship and how manufacturing is. Now, the fundamental characteristics of all existing manufacturing processes can be understood by considering the following basic aspects: energy type, mechanics of material removal, energy source, manipulation and control. Now, through innovative exploitation of relevant engineering science involved, many non-traditional manufacturing processes have been developed. So, energy types are mechanical, electrochemical, chemical, and thermal. Mechanics of material will be plastic shear, erosion, ion displacement, corrosive reaction, fusion and vaporization. Energy sources could be mechanical motion, mechanical fluid motion, electric current, corrosive agent, electric spark, high-speed electrons, powerful radiation, all these. So, manipulation and control technology help in automating manufacturing, you all know. The revolution in electronics and computer engineering has drastically changed the manufacturing scenario, and we consider now whole manufacturing is now computer integrated. But still fundamentally there has been no major change, because now we need a paradigm shift. You all recognize what is this. This is the Kailashatam Kilora. These are the human beings. So its scale is huge. How it was done? It is one piece of stone which was cut from the top, and this whole intricate complex has been produced. Each small figurine, each step, each window, everything from one piece. And that is our conventional method of producing shapes. But the opposite thing is that you build up from bottom by adding small pieces, and you get the whole. That is called the bottom-up approach. So, bottom-up approach is you all know that you make a CAD model of your shape, slice it computationally, and then generate it one by one. And you know these are the STL machines, etc. And rapid prototyping, digital manufacturing, all these things have come up basically. Now, the bottom-up approach is going to decide the course along with the futuristic manufacturing activity will grow, and the following slides symbolically indicate the progress of various engineering science areas helping the necessary innovations to achieve many exotic processes and engineering applications of the acquired knowledge. This will help in what is called translational research that will make it feasible to integrate the research labs and the application area. Say, the traditional engineering subjects, they will continue, but more and more physics will come in because of the simulation, atomic, we want to start from the atomic interaction level. Chemistry will give you self-assembly and such things. Mathematics and computation for extensive simulation and modeling. As you have seen, this will be extremely extensively simulated. Life science will come because life science has taught us how to self-assemble. And the engineering of the coming future days will be a mixture of all these. And there will be materials engineering, mechanical engineering that gives us traditional manufacturing. Electronics computer engineering gives us modern automated manufacturing. Physics, chemistry, polymer science gives us advanced manufacturing. And principles of life science, when get integrated, gives us the futuristic manufacturing. And the new areas of engineering science, I just mentioned few. You should think very carefully and try to incorporate at least slowly into our academia these engineering science branches. So the knowledge base for conventional engineering is this: simulation and molecular engineering, synthetic biology, smart macromolecules and intelligent materials, fabrication by self-assembly of materials, artificial intelligence, self-learning, self-correction, and ultimately self-replication. all these areas is going to be your knowledge base for new era engineering and translational research. The primary components of the futuristic engineering in another couple of decades' time will be this. Basic features will be miniaturization. I will not go into details because we don't have that much time. Then massive parallelism, just like the living objects, bottom-up fabrication and self-assembly based manufacturing, embedded biochemical energy source and control electronics, and smart materials. You know, many new energy sources will come. The nature, for example, in many cases, they use sun's energy, how plants use it by photosynthesis. So who knows that in future, after another 50 years, you will make many machines which will run on the basis of photosynthesis. So what will be the result? Our industry will produce oxygen and clean the atmosphere. Just the opposite thing what we are doing today. There are some almost beyond our imagination the kind of thing which will happen. So all the above mentioned fundamental changes can be achieved only through appropriate innovation, and that will require the new era engineers to possess a very strong understanding of the relevant engineering science. Then only the engineers will be capable of facing the challenges posed by the onset of next industrial revolution. What I give an example, just the last thing to tell you. You know, in cricket fielding, I saw one very funny fielder in our campus. He used to always run towards the ball, and both of them used to reach the boundary at the same time. That is not what is desired. A good fielder does what? He preempts the location where the ball is going to reach, and he wants to intercept that. The same thing in technology development. If we continue to only follow the existing technology, we will never be ready. So you have to preempt that after 20 years, what will be the areas in which the technology will reach, at least parts here. And we should try to reach that directly through our innovation, through our academic programs and research activities. So, thank you for your kind attention. If there are some questions, I will answer. Thank you very much.
Thank you, sir, for such an enlightening talk. And we express our gratitude towards such a wonderful talk. If any questions are there?
How is it going on?
It's going on very fine, sir. Very nice. We are missing you.
So sad not to do.
Yeah.
I had all plans to do. I have to leave tomorrow for Gandhi.
Okay, no problem. Next time we are organizing it right indoors. So I hope that you will come there.
Sure.
Thank you, sir.
Thank you for your kind invitation.
Thank you.
Thank you once again, sir, for such a wonderful session. The AIMTDI team will send you a memento on your address.